Okay, this is just a continuation of the last absolute motion example, and what we're going to do now is we're going to define our angle on this diagram. So we're going to define this in here because we've set up a rotating frame of reference along these axes. So this is a y-axis and this is our x-axis, and they're rotating. We're going to set this up, the angle between the absolute frame of reference and this y-axis here. So this rotating y-axis is going to be angle beta. So that beta, the angle beta, is going to be the angle beta is going to be, so we've defined this as being OA or OA bar, and this is being R. So beta equals sine beta equals OA on AC, right? And AC is our R. So we're looking for the sine inverse of the ratio between these multiplied by the sine of the angle here, representing this, whatever this angle AOC is. So if this angle is 90 degrees, we would just have the sine inverse of OA on R, so it's proportional to what this angle AOC is in here. So if the angle does, like, so say if we had the line, so OA was perpendicular to OC, then this AC in here, so this is C, this is O, this is A, but this A is free to move like so, so it end up being a non-right angle triangle. So what we do is we multiply this sine inverse of OA on R, so this is our beta in here, so we multiply the sine inverse of our OA on R to get the angle, because sine beta, when at 90 degrees, so specify at 90 degrees, sine beta is equal to opposite over adjacent, which is OA on R. So at 90 degrees, beta equals sine inverse of OA on R. But when this angle increases, what happens? We have to multiply this term by our angle, so by the sine of our angle. So sine basically represents a ratio. So if it's not, so if beta, so if this angle in here is not 90 degrees, so like so, beta equals the sine inverse of OA on R multiplied by the sine 90 plus theta. And that's equal to, because we know what the magnitudes of OA and R are, that's equal to the sine inverse of 100 on 361 times sine 120. Because it's at 30 degrees. So therefore, if we plug that in the calculator, we get beta is equal to 13.9 degrees, or 13.90 degrees. If we define the angular velocity of our bar OA, so that bar that's rotating, we can define that as being constant. So as a vector quantity, omega 1 is equal to theta dot k, which equals 3k radians a second. And the position vector from point O to point A is represented by our position vector OA. OA is equal to the magnitude of OA multiplied by the cosine of our angle plus beta in the I direction plus sine of theta plus beta in the j direction. And that is equal to, we know what our beta was, we've already found beta, so that's equal to the magnitude of OA, so that's 100 millimeters, multiplied by cosine 30 plus 13.9, which is 43.90 degrees in the I direction, plus the sine of 43.9 degrees in the j direction. We end up with a vector with respect to position, which is 72.1 I. This is at the instant, plus 69.3 j millimeters. And we can determine the velocity of point A to be, we can determine it to be omega 1 cross r of OA. So we know omega 1 and we know r of OA.